Okay, yeah, good. What we were doing was we were doing axioms of quantum mechanics. So let me recall. So the zero axiom, I don't know why I call it zero. So, I mean, for any quantum system, there exists a Hilbert space over C. Now, this I have to qualify a little bit. The existence of Hilbert space is actually not absolutely necessary. You can have quantum mechanics starting with other things than Hilbert spaces. For example, you can start with C-star algebras. You can start with von Neumann algebras. You can start with Poisson algebra. You can start with, not Poisson, maybe not the right. You can start with at least C-star algebras and von Neumann algebras. Maybe even they are better, more invariant and more functorial way of talking of some aspects of quantum mechanics. But I should say 99% of people use Hilbert spaces. So I think this is a good start.
Are the other formulations physical as well? Like they correspond to
yeah, they are physical. Well, they are physical. And there is another one actually starts with deformation quantization. That's also, yeah, I mean, this is, yeah. So there are various approaches, but I would say 95% of the things it starts with a Hilbert space over complex numbers. So that's something.
Is there always sort of like correspondence, like model your mechanical system on a C-star algebra or whatever? You always build the corresponding Hilbert space for that system, and vice versa, or?
Under some conditions, if you have a state, you can go on and construct the Hilbert space using Gelfand-Neymark-Seagull construction, the GNS construction, so-called. So the lesson is that Hilbert space emerges from more primary considerations, more fundamental considerations. And that's actually one of von Neumann's ideas. He wanted not to start with Hilbert space, with other things, and then you drive the Hilbert space. So sometimes he started with certain types of lattices. So these are lattices of measurements. And then he shows that under some conditions, those lattices are necessarily are lattices of subspaces of a Hilbert space. So Hilbert space emerges. Those are some nice theorems, difficult theorems on projective geometry in infinite dimensions, things like that. So there are indeed, there's a whole sea of mathematical results around those approaches. But for us, it's just this one.
Maybe that's one good small.
Yes, yeah.
But there's this unbounded theorem where if you have like your low computation relation, you can represent it as a C-star algebra or something like this. You look at the representation for the C-star algebras, and then you get like a Hilbert space out of that construction somehow in the end, or is this kind of unrelated?
No, I mean that Stone-von Neumann theorem says that essentially uniqueness of representations of canonical commutation relations on Hilbert spaces. So these are unitary representations of CCRs. So they are not like, that's more or less like uniqueness of representations of CCR with finite degrees of freedom. In infinite degrees, that's totally different. They're not unique. That's a very interesting. This was a nice question. Good question. Okay, so then axiom 1 was that states of the system So these are trace class positive, in other words, non-negative rather, operators with trace 1. So these are also known as density matrices. So these are basically go from H to denote H, go from H to H. Go rho is bounded operator, bigger than equal to 0, and is also a trace class operator. This trace is equal to 1. So these are the states of the system, and then pure states, as we discussed, these are rank 1 trace class operators. So these rows are density matrices, and this rank of row. Okay, row basically is equal to projection to U belonging to H, different from 0. So these are rank 1 projections. These are pure states, which you can also think of array, a one-dimensional subspace of the Hilbert space, but that's exactly what it is. Or unit vectors modulo phase equivalence. So these are states of the system. And then we also add axioms for now. Okay, so I believe we stop there. So now today we're going to discuss observables. So what are observables? So observables are in general unbounded self-adjoint operators on H. Unbounded. I mean, in general, unbounded self-adjoint operators on H. So this is a technical term. Let me unpack this, its meaning. So first of all, what so note such a thing by A. So when you are discussing unbounded operators on Hilbert space, you have to allow yourself the domain of this operator not being the whole H Hilbert space, but some dense subspace of this. So A from domain of A to H. So this is a linear map, first of all. It not be continuous, but as I said, we assume that domain of A is dense. So domain of A inside H is dense. Now, you may ask why we need dense. I want you to think about it yourself. What you gain if you don't assume it is not dense, and you see that you don't gain much. Actually, it's a good assumption. If you have a domain, you can always consider its closure. The closure of that domain is going to be a Hilbert space. So then your problem is on that Hilbert space. But then in that case, you may get into a situation where your observable is going from one Hilbert space to another Hilbert space, which is not good. You don't want that. You want to go from same Hilbert space to itself. Another point is that if domain is not dense, then this operator is not defined on a big enough set. So technically, it's very, very useful, and it's actually essential to assume that domain of A is dense. That's kind of important. So this is an important technical assumption. This is linear map. So we can forget about self-adjoint and these things for now. So for any such A, we can define an operator called A star, adjoint of A. So we define another linear operator. We call it A star from a domain, which I call it domain of A star, to H again, as follows.
Maybe I think I missed it, but why are you restricting against that at all? Why can't we just make it all H?
Oh, because you don't get interesting operators that way.
Oh, okay.
You're going to miss out a lot of almost all of quantum mechanics is based on unbounded operators defined on dense subsets.
Oh, okay. All right, interesting.
Hardly any operator that's of interest in quantum mechanics is defined on all of H, except these density operators, which are defined. Oh. That's true. I mean, what I said was an exaggeration. I mean, there are operators like unitary operators, which are symmetries. These are bounded operators. But observables, they have to be. They better be.
Is there like a physical reason why or not?
I can give a decent example in my felt.
Okay.
So pretty standard quantum mechanical systems like LTR. And the momentum operator is d by dx.
Yeah.
But not L2, all L2 functions are differentiable, so you can't apply it to other.
So you can't like.
Yeah.
Okay.
So you need a dense domain for your momentum operator.
We'll see a lot of examples very soon indeed, yeah.
And
exactly.
So you can't make like sort of measurements in physical. I'm trying to understand the physical world too at the same time.
Yeah. I mean, that's the way life is. Yes, indeed. But so let's start with this math issue now. I want to define an operator called its adjoint that goes from domain of A star to H. First of all, I have to define what is domain of A star. Well, we can define it like this. Domain of A star is the set of all Y belonging to H such that the map X to inner product of X and, T of X, T of A of X and Y, this map is actually a bounded map. Is bounded on domain of A. Okay. So the domain of A star is the set of all vectors in the Hilbert space where this map, this is a linear function of from domain of A to C, right? This map, I demand this map to be bounded. Well, I mean, this is obviously a subspace. Domain of A is obviously a subspace, right? Certainly 0 is there because if you have 0, you get 0. There's at least one point which is 0. If y1, y2 are there, the sum is there, scalar product is there. I mean, scalar multiple by constant others. So this domain of A star is a subspace of H. So once you have that, then what can you do? Then we can use Riesz representation theorem. Riesz representation theorem. By Riesz representation theorem, so what we can use Riesz representation theorem in the following way. First of all, we extend this map from domain of A to all of H because it is bounded. It's a linear map which is bounded on a dense, so here is density is important, which is defined on a dense subspace of the Hilbert space. So has a unique extension to a bounded linear operator on H. So once you extend it, okay, extend it to a bounded linear operator on H. There exists a unique extension. This is clear. And then by Reed's representation theorem, there exists a unique vector. I call it T star of Y. Such that you can represent this linear functional as inner product of X with that function. X and Y, sorry, X and AX, sorry. Y is equal to X and T star of Y. Now this holds for all X in domain of A and for all Y in domain of X. So, yeah, as I said, you see, this gets technical now. So, this is the only way. This is the only way we can define the adjoint of an unbounded object. This generality. Okay. So it satisfies the adjoint property. In quantum mechanics, in physics literature, this star is denoted by dagger. It's not usually, but we never use dagger. We use a star. Okay, so this is I just defined the adjoint of an unbounded in general unbounded operator. Questions? Oh, A. Oh, sorry. This is yes. Yes. The domain of A star may be zero, maybe as small as zero. It's quite possible. Domain of A star to be as small as zero. Okay, so we are defining these observables. Questions. How do you see it defined?
I've seen it defined basically, you take the domain of A star to be all of the Y such that that equality holds.
You have to use Reed's representation. Yeah, without that you can't. What is A star then?
So it's supposed to be like basically the unique solution to that equation.
Why that solution exists?
Okay, yeah.
That's Reed's representation theorem. Yes. Okay, so it's so that's the adjoint operator or in general unbounded operators. Now we can define what self-adjoint means. So then definition now of self-adjoint. That's an important definition. A is called self-adjoint. If, first of all, domain of A star is equal to domain of A, and A star of X is equal to A of X. for all x belonging to domain of A, which is also equal to domain of A star by our self-adjoint. So the famous equation Ax y equal to x ay. So we just say axy equal to xay is implied by this for all x belonging to the domain of A. For all x and y actually belonging to domain of A. Okay. So there are two conditions. They should not be underestimated. I mean, this condition is about equality of domains, and this condition is that on that domain, equal domain, they satisfy this adjunction formula. So now, the question is how on earth we are going to prove that such an operator is self-adjoint. The answer is, in general, it's very, very hard to prove operators are self-adjoint. And the best way to approach this is to start with some examples. So, any questions? Okay. So now let me. So we are still discussing the meaning of this second axiom. The observables are unbounded self-adjoint operators on H. So let me now erase this. And so there is a definition of an type of operator which is weaker than self-adjoint, and that's very often easier to verify. It is satisfies that condition, and usually it's mistaken with self-adjoint. So let me tell you what that is. So definition: an operator A from a domain of A inside H. Again, I'm assuming it's dense to H. It's called symmetric. We call an operator symmetric if Ax y is equal to x ay for all x and y belonging to domain of So this condition is much easier to verify. Okay, first of all, a simple observation is that self-adjoint implies symmetry. By this, I mean, if your operator is self-adjoint, I just erase that statement, then they are symmetric for sure. But by no means the converse is true. The converse need not be true at all. And that's the confusion. Most of literature, people in physics, when they say the operator is self-adjoint, all they care, all they check is this condition. But that's not mathematically enough to say things about quantum mechanics that we want to say, as we'll see soon. So let me give you an example now, just a simple example. Let's take H, or Hilbert space equal to L2 of R. So by the way, this is the Hilbert space of a particle that's moving on the line. can move from minus infinity to plus infinity. The quantum mechanical particle that exists on the line. That's its Hilbert space. Now, for this, let's take a domain of A to be C in C of R, for example. So this is smooth functions with compact support on the line. And obviously, this is inside L2 of R. This is obviously dense. I mean, it's not obvious, but we can prove that it is dense. It's not so difficult, right? Okay, now the operator that you were talking about, Jeremy. So the operator of momentum, for example. So A equal to momentum operator. So in quantum mechanics, we usually write it as 1 over I h bar ddx. Okay. So among 1 over I h bar ddx, this goes from C infinity C of R to H. Now this operator is symmetric. A is symmetric. Why is it symmetric? I mean, well, what does this mean? This means that basically inner product of A, F, and G, I'm saying, is equal to inner product of F, A, G for all F and G belonging to C infinity C of R. But so I didn't tell you what the inner product here is, but you can guess. This is the same thing as 1 over IH bar F prime G bar, because we are talking about complex valued functions. The claim is that this is over R. The claim is that this is equal to integral F 1 IH bar complex conjugate and then G prime yes, and then G prime complex conjugate. So I should put the dx here. So integral, and you see integration by part implies this. So integration by part. So this is okay. And notice that it's very important to put the factor of I here. Without this factor of I, this won't be self-adjoint. This would be skew-adjoint. The factor of H bar, Planck's constant divided by 2 pi, is a physical factor. That's important, but not mathematically for now. And I put 1 over I, not I. 1 over I is more standard. And it makes more sense to put 1 over I. But with I is also. Anyhow, so this operator is symmetric. That's all right. It's fine. But this operator is not self-adjoint. This guy is not self-adjoint. But A is not. So what is the reason for this non-self-adjointness of this guy? A. Domain of A, first of all, you notice that there is something very easy to check, that domain, if asymmetric, any symmetric operator, as I defined it. Doesn't have to be this one. For any symmetric operator, domain of A is always inside domain of A star. That's from the definition it follows. Domain of A is inside domain of A star. But this is clear from the definition. Domain of A is inside domain of A star. But in this example, domain of A star is way bigger than domain of A. Now, it contains, for example, the following type of vectors. C2 functions with compact support is there. Is bigger than e.g. C2 C of R. C2 functions with compact support are there. Because if G is there, you still have this relation. You can still apply integration by part to those, and then you get the equality. Okay, even C1 functions with compact supports are there. It's even bigger than that. So this is not, and this is a strict. So the conclusion is that A is not self-adjoint. The A that I defined here. So let me put it like this: A equal to 1 over IH bar, the momentum operator, IH bar dx. And you see, there is some arbitrariness in this game. I just picked my domain to be C infinity C of R. I mean, I could have taken something much bigger, which would be Schwartz class, for example. Or I could have taken functions that go to infinity and they are in C2, for example. Go to 0 rapidly enough and they are in C2, or they are in C1. So there is not a canonical choice for this. Domain of A right now. We cannot see what is the right nice domain for this function. You see? That's the complication. Any questions?
Will we see one later?
Hmm?
Will we see a canonical choice later on?
Well, very soon I will tell you what.
Oh, okay. You seem to hint to this, so I wasn't sure if we ever.
Yeah. This yeah.
We're kind of in a weird situation where we know what we want our operator to look like. We don't want this derivative operator. But we know we want the operator to look like right now. But there's no obvious way to pick the domain from knowing the form of the operator. Picking the domain can change the operator. And then there's like wanting to do this Vegas stuff. Is there an obvious way to like pick the domain to know the form of your operator?
Because we are in the wrong world in a way, from the point of view of momentum operator. We are not living in the right world. We are in position space, and in position space,
Oh, so you want like Fourier transform?
yeah, we have to Fourier transform, go to momentum space. That's the space where this P, this A actually is very natural. And then in that case, you can immediately see what is the domain. But if you come back to this strange position world, from the point of view of this guy, we are living in the wrong world, actually. We are in position space, and that's bad. We have to go to its own space, which is momentum space. I will define it quickly. So in any case, but there is this issue that actually started with von Neumann. Von Neumann was more or less the first person who understood these things completely and started developing theory of unbounded operators and extensions. So what von Neumann proved, one of the things that he proved is that, for example, this operator and much larger class of operators, they have a unique extension to a self-adjoint. So I won't prove it because it just takes us into functional analysis of unbounded operators. The fact is that there exists unique extension of A equal to 1 over I h bar ddx from domain of A. I define its domain to be rather arbitrarily from, say, C infinite C of R to L2 of R to a self-adjoint operator. I denote it again by A. This is the momentum operator from domain of A. Well, this definitely contains, but it's much bigger than C infinite C. So this domain now is some mysterious domain. It's just an existence. Someone says that, hey, there exists this much larger subspace, linear subspace, where you can define this operator and it's self-adjoint over it. So this is what this. So this A is called momentum operator in quantum mechanics. Momentum operator. This is in one dimension. Now, there is a kind of analogous operator. It's called position operator. And X equal to multiplication by X operator. So this sends F to XF. And most of the time, we don't even care to write MX, we just write X. So F is sent to this. Now, this is called position operator. Now, again, I have to define a domain for my position operator as well. So well, I mean, let's take B to be this. So domain of B, again, I rather, maybe arbitrarily, I don't know, I can say the domain is going to be the set of all F belonging L2 of R, such that actually X, F of X, belongs to L2 of R. Because we are multiplying this, right, by this X, and I want this to be again in L2 of R. So this one is very canonical in a way. This is kind of easy to guess, right? We want to, this is the largest possible domain, by the way, for this operator X to be definable, right? Because you want to land here, so you better have this condition. Right? And in this case, actually, you can show that this is a self-adjoint. This is with this domain is self-adjoint. Yes, self-adjoint. Now you know what the solution to example 1 is. This example is. Back to momentum operator, you can say the domain of momentum operator, where you can extend it, is the set of all functions whose Fourier transform have the property that if you multiply by P, or Xi, the Fourier, the variable, that's in L2 of Fourier space, momentum space. Now, in terms of the function itself, we don't have nice condition. But that's very strange. I don't know any easy, reasonable condition in terms of the original function f that tells you that its Fourier transform is such that it's in the domain of multiplication of it. That's one of the strange things about the board, maybe. Some issues we can see in this picture better than the other, and vice versa.
Unique extension of that.
This one?
So you read that fact. There's just a unique extension of this. You're going to see them.
Yes. Yeah.
That's equivalent to the domain you're describing.
That's well, yeah.
You know what I mean?
I mean, the idea is this differentiation becomes multiplication by x if you go into Fourier. So then you can guess what it is.
I guess what I'm talking a little bit is that unique extension. What if you pick the different domains? Like what if you pick C2 here, Schwartz class functions?
Yes.
Same unique extension.
Same unique extension. Yes. They all have same unique extension. Yes. And this uniqueness is not obvious at all. It's some lot of well, some of them are small pieces of the math, some of them not so small. Are very clever arguments you have to put together to develop some theory of unbounded operators. But we should be aware of issues. So symmetric, you compare it with self-adjoint. Symmetric is easy. Physicists usually check symmetric condition using boundary value conditions. The self-adjoint is much more delicate. And it is self-adjoint that you need in order to introduce dynamics. So now let me go to an example which is like finite dimensional and kind of another example, but it is still important. So this example is spin 1/2 Hilbert space. So this Hilbert space is also sometimes called now qubit because of quantum computing and all that. It's really H equal to C2. And in this case, you know all of self-adjoint operators here, right? So what is first of all the morphisms of H, or rather, I mean, bounded linear operators of H. This is just in2 of C. I mean, every operator, every linear map from H to H is bounded because this is finite dimensional. So algebra is enough in this case. There's no need for analysis here. Now, self-adjoint. So A belongs self-adjoint. So these are observables. The observables are 2 by 2 self-adjoint matrices. And there is a very nice basis for this space, which is Pauli spin matrices. So Pauli spin matrices. So they are denoted the sigma 1, sometimes denoted by sigma x, which is, do you remember what is sigma x or sigma 1? Sigma 2 combined with sigma y is denoted by its, yeah, 0. Yes, very good. Yes, x 0 minus I 0, and sigma 3, which is sigma z, which is 1 minus 1 0 0. And there is also sigma 0, which is just identity. So these four self-adjoint matrices is a basis for all self-adjoint operators on two-dimensional hyperspace, right? So any A, we can write it as some, I don't know, Ni sigma I from 0 is Ni belongs to all. That's a nice representation. Any self-adjoint thing. So this is very useful matrix representation. Any question? Okay, so that's good. Now let me give one final example. That's for observables, angular momentum. So these are quantum mechanical angular momentums, right? So what are they? These are some operators A from L2 of R3. I mean something is Li from L2 of R3. Well, not L2 of R3, from domain of Li inside L2 of R3 itself. This is the Hilbert space. Okay, so they are obtained from classical angular momentum in a kind of more or less standard way. So do you remember the classical angular momentum? So think about it like this. You have a particle that's moving in space, and you have a coordinate system over there, and you want to measure the angular momentum with respect to that coordinate, the origin over there. So what is the angular momentum of a particle? Obviously, it depends on the speed, right? It depends on the speed and depends on the position. And L, say the angular momentum, the classical angular momentum, is equal to, can you tell me what is it? Yeah. It's the cross product, right? The cross product. Cross product of R, the radial, the radial, the vector by P, momentum vector, which is NV. This is NV. So if you compute this, so I just don't remember. I want to derive the formula. This is the kind of. So this is I, J, K, and then here I have got so X, Y, Z. So this is R, and this is the momentum. I can just write M. Well, the components are denoted by NVX, NVY, NVZ. Okay. So this is equal to, for example, I times X. So this overall factor M, and there's I times x vy of y dz, sorry, minus z vy minus j something plus k something. So from here now you can see what we should do, because this is position, this is momentum, and we know how to quantize position and momentum by previous example. So we can just say, okay, now this guy, the quantum mechanics. So now I'm using, sorry, this notation I'll have just to not to confuse it with this L. The quantum mechanical angular momentum is going to be, so in x direction is this operator. Y, now here this is the momentum, so this is going to be equal to bar, and then I've got y d z they do with this I is not, it's not
Yeah, it's
that
not that
I.
I, yeah.
Nothing to do with that. Sorry.
What about M though?
This is the how.
What about M though?
What about M? Yeah. What should we do with them? P is equal to MV.
Yeah, but your P is going to, like, what I would do is I would write the, instead of PZ times M, I would just write PZ quantize. PZ, you get that I H bar. So it just carries through.
Yes. So I should put M here, you're saying?
No, I think it's already,
Oh,
it's already fine the way it is, because when you are quantizing the operator, you have down,
that's yes.
it's already accounted for.
So I just put it like that, and this minus Z d dx, ddy, sorry. And then you can write like that y. So y goes to z, z goes to x. They're cyclically rotating now. Minus z goes to x, y goes to z. And then at z is z goes to x, x goes to y, goes to y, z goes to. So we've got these three linear operators with coefficients like that. So they are all going from domain of L hat to L2 of R3. Okay, and now these operators, the way I've written them, they are obviously symmetric. These are symmetric operators. This is all right. You can check these are symmetric operators. Do you know why they are symmetric?
Without checking this, the reason.
So some quick reason, yeah. Yeah, so let's go back to linear algebra. Just imagine you're just dealing with matrices, okay? Just to get a clue. So if you're dealing with matrices, if you have two self-adjoint matrices, okay, two self-adjoint matrices, if you multiply them, do you get a self-adjoint matrix again? I mean, in matrices, symmetric and self-adjoint are the same.
So, yeah.
So you get?
Yeah.
No.
What?
You don't.
I mean, A times B star is. B
You see,
star,
you
A
have
star.
A star.
Oh, yeah, of course.
Equal to A here.
That's-
B
Yeah, they
star
don't think you.
equal to B does not imply that a B star equal to a B. This does not, it's not implied. Unless they commute. Now look at here. Look at here. You see, the operator multiplication by y is symmetric. You know that. Also, 1 over IH bar dBz is symmetric. It's also symmetric. And they do commute. These two operators, because they do commute, they don't fill each other because this is with respect to z, this is with respect to y. So this part even already symmetric, and this is also symmetric and the same. So checking that this is symmetric is easy, knowing that they commute. But then showing that there is this unique self-adjoint extension, it's a lot of work. But we just assume that. Okay, very good. So these are the angular momentum operators.
Rather than.
Or the domain of this.
Yeah, you know the domain, but I mean, based on what you said before, you know the domain. Like the momentum operator, and the position operator, and this is like the linear combination plus composition, it's two operators, so. You figure that out like this.
You can figure out some domain
Oh,
to render it symmetric.
but.
And for example, smooth functions with compact support, that's enough.
With the-
But then proving self-adjointness is a different game. And you have to use some general facts. That's the. Any other questions? Okay, so now, so we are done. Okay, now we discussed the meaning of observables. Now I want to write some three. So this is dynamics. So now we want to have a rule that tells us how states of the system changes. So basically, we need a rule that tells me that if my system at some time is in some state rho, then how it will evolve in time, in future, and perhaps where it was before present time. And this equation exists. So for this, need a self-adjoint operator called Hamiltonian. Or energy operator. So this is H. Again, this has some domain. to start, in order to talk about dynamics, we need this Hamiltonian or self-adjoint operator, which is called also energy operator. So if you compare to the case of classical mechanics in Hamiltonian picture, in symplectic picture, over there also we had a function, real-valued function called Hamiltonian of the system that gave us the energy of the system at the particular point, right? So this has to be given. Then the equation is like this. So this is Schrodinger's picture. So this is I H bar rho dt equal to commutator of rho and H. So now we have to really think about it, see what it says. So basically, this is an equation on the state space, right? So if you have a point, so imagine there's this infinite dimensional huge state space. So if you have some rho zero, if this equation defines a curve rho t that at time zero is at rho zero, this is the initial condition, and it satisfies this differential equation. Now, have you seen something like this before? A differential equation similar to this in the classical case? Yes, this is comparable to Liouville's equation, where so this indeed should be compared with Liouville's equation. In classical mechanics, which said that basically the rho dt equal to Poisson bracket of rho, and there was a Hamiltonian there which are also denoted by capital H, but maybe I should have denoted it by little h. That's it. This was the Hamiltonian. This is the. Now, what is this rho? So over there, the way we proved it, this rho was a function on the phase space, but then we can think of it as rho of Qs and Ps, or T rather. So the idea is that if you have an observable like rho, a density function, but could not. And if you study the chain variation of this observable along a path, we showed that it actually satisfies Liouville's equation. So this is morally a bit like this, but there are two big changes, two big changes. First of all, there is an H bar. There's no H bar. And there's I here. Commutator is changed to Poisson bracket. Yes. Okay, so this is not the way Schrodinger equation is taught in physics most of the time, and again, 99% of cases is not what Schrodinger wrote. But this is the best conceptually kind of clearest presentation of Schrodinger's equation. Now, what about the standard Schrodinger equation? The standard Schrodinger equation gives us the equation for evolution of pure states. So for pure states, So imagine, okay, so we know what pure state is. This is projection operator on some ray U. You can have a curve in the space of pure states in the following way. You can just choose a curve of vectors in the Hilbert space and look at projection operators on that. So, e.g., E of ut. So in physics, we never write ut, we just write psi t. Then Schrodinger's equation for this evolution of this psi t is the following: IH bar d psi dt equal to h of psi. I don't know, maybe that's the one that appears on Schrodinger's grave. I'm not sure, on gravestone.
Is that how he originally wrote it for pure states?
Well, he did not talk about pure states. He just had only states. For him, states were just these wave functions psi.
Okay.
And he just wrote this equation.
But what he calls states, we now call pure states. Right?
What's that?
What he calls states, we now call pure states.
What he calls?
What he referred to as states, the psi, is what we call pure states now, correct?
Even less than that.
Oh, even less. Okay.
Because he refers to psi or u as states.
Okay, I see.
I think then maybe he himself realized that it doesn't matter, it's fixed only up to a phase. If you multiply it by a complex phase overall, it's the same thing, because I think this came 1 year after Schrodinger. It was by Max Born when he did this measurement axioms, which I will recall. So that's what happened over there. But if you want to write an equation for pure states, this is not the equation, because this is in terms of vectors. This is a special case. And by the way, is this equation equivalent to that equation for pure states? I mean, if you apply this to pure states, do you get this equation? I mean, here, so imagine you have a psi that satisfies this equation. Then you can prove that with rho equal to p psi t, rho t satisfies this equation as well. But not vice versa. I mean, one reason is that this h actually here, if you change h by some fixed amount, you get the same equation because they cancel. Not here. So I don't know. There is some subtlety in relation between these two pictures. And this all has to do with the fact that most of the time we confuse pure state with a vector in the Hilbert space. It's not a vector in the it's a line, one-dimensional subspace of the Hilbert space. And they are very different. Okay. So any question? I want to finish in 5 minutes.
So this equation saying it doesn't apply.
It does imply.
It does apply that, but not this.
Not what.
And that's because if you add a constant term to h, and so
You get the same rule, but not here.
physically, this distance equivalent though, I kind of.
It looks like you're shifting the ground state or something like that.
Physically equivalent because
Could be, but I don't know what happens to the solution here if I add a constant term. Well, I was just too lazy to look at what the situation if you had a constant. It's not a straightforwardly, they are not equivalent in a straightforward manner, at least maybe.
Maybe Jared's point, or maybe that's why people confuse more to this too, because they only care out they only care out gently level differences. So they're just like, oh, use this thing for our purposes.
You use that big bang a lot. So
Yeah.
making manipulations easier. And like,
Oh yeah, sweeping the infinities under the rock.
yeah, you can do that by like shifting your H1 by constant.
Yeah.
Like certain part of that.
Yeah.
So when Schroedinger was thinking about this, was he thinking about psi as like L2 of R, or was it more general?
No, I think it was in L2 of R. I don't know if he used the word L2 of R,
Right.
but or notation, but he was thinking. So his first paper is called Quantum Mechanics as a Boundary Value Problem, and boundary values for him was this decay at infinity. I'm not sure he was very precise about the nature of it.
But he was thinking about functions on the line.
He was talking, he was thinking about functions on the line. But interestingly enough, psi for him was real value at first. He did not have complex waves, but then I don't know what happened. This is a historical thing.
Probably
It's
switched the interpretation after, and that interpretation requires complex.
I don't know.
I-
Probabilistic interpretation came after, a year after by Bohr, that's true. But why still complex numbers are demanded? I'm not sure.
Using the Schrodinger equation, get like a probability current, and it only makes sense if your wave function is necessarily complex.
I see. Okay.
So,
Yeah.
right on.
But complex makes it. Another thing it was that this psi, I mean, that doesn't have physical reality. It's not. I mean, it's not something that you can observe somehow. The only physical reality is this probabilistic interpretation of psi. I mean, the value of psi at any point doesn't make sense at all. There are some discussions like that. Again, there half of it, I don't know, part of it is philosophical, so I don't.
Where does the randomness come in?
Oh, it comes in the measurements.
Oh,
next
yes.
axiom.
Gotcha.
It's coming. Yeah, it's coming. So I was going to talk about Heisenberg's picture after this, but this has to wait for. So we'll talk about Heisenberg's picture and the measurement axiom, and then we show that in some sense they are the same. Okay, guys, thank you very much. So I just end this now.